In this section, our main goal is to find the derivatives for the arctangent, arcsine, arccosine, all the inverse trig functions. And along the way, we will talk more generally about how the derivative of a function at a point is related to the derivative of the inverse at the corresponding point where you switch the values of x and y. So to get started, let's take a look at this function, and if you want to, you could probably figure out what this function is, but I just want to think about this as a general function, f, that's in orange there, and its tangent line at the point 2, 1. So for f, I can see f of 2 is 1, since I have that point 2, 1 there. I can also see f prime at 2 is whatever the slope is of this green tangent line. So it looks like I'm going up 1 and right 2. So the slope at 2 is a half. And I want to think about what is f inverse at 1 and what is f inverse prime at 1. So I want to know what's the value of the inverse at 1 and what's the value of the derivative of the inverse at that same point 1. And we know that f of 2 is 1, then f inverse of 1 is 2, right? Because we have the point 2, 1 on the graph of f, we'll have the point 1, 2 on the graph of the inverse. So that's why I was picking on 1, because that was the output for the original function at 2. And we can remember that sketching the graph of an inverse of a function just means swapping all the values of x and y and creating a new set of points. So this point here on f is 1, 0. So I want to make sure that I have 0, 1 on f inverse. I have 2, 1 on f, so I want to have 1, 2 on f inverse. And I can see this is 5, 2 on f, so I want to have 2, 5 on f inverse, and that's a little bit above my chart here, but we can see that this would be a sketch of the graph of f inverse. Right, so all of the x's and y's are just flipped. So if we know that for this line, the change in y over the change in x is 1/2, then when we reflect everything across the line y equals x, the change for the slope in this other line is going to be exactly the reciprocal, which should be 2 over 1 instead of 1 over 2. So just like the points, the coordinates themselves get changed, the x and y switch, the ratio for the change in y over the change in x will also just be flipped over. So here, the slope of this line is 2. And that tells me then the derivative of the inverse function at the point 1 is 2. And that's just the reciprocal of the derivative of the original function at that point with the x and y coordinates swapped. Right? And so we can see, well, that's just the reciprocal of the derivative of the original function at the inverse of 1. Right? So if I know the original function slope at the point with the that would correspond to the point where we want to have the derivative of the inverse, we'll just take the reciprocal of that original function derivative. Right? And that's exactly what this theorem is trying to say. The notation makes it look complicated, but it's just saying if you know the derivative of a function at a point, then you can find the derivative of the inverse at that point with the x and y swapped by just taking the reciprocal of the derivative that you know. So let's see how this will work in another example. So this is saying, okay, use that theorem that relates the derivative of a function and the derivative of its inverse, at the point where the x and y are swapped by picturing g of x equals square root of x plus 4 as the inverse of another function. So we want to figure out what's the function f whose inverse is square root of x plus 4. Right, so we're saying I have the inverse function. I want to know what the original function is. Well, keep in mind that if we have the inverse and want the original, I'm just trying to find the inverse of this function. So I would think to find the inverse, I'm going to do x equals square root of y plus 4, and I'm going to solve it for y. So I would square both sides and subtract 4. And that would be my original function with a slight modification. If I think about how functions and inverses work, I know that a function and an inverse both have to be 1-to-1. So if I'm looking at the square root of x plus 4, that's the square root graph shifted 4 units, not to the right, 4 units to the left. So roughly looks like that, right? And f of x, x squared minus 4, would be a parabola shifted 4 units down. And I can see that that parabola is not 1-to-1. And I want the domain for f to be the range of f inverse, and the range for f to be the domain of f inverse, right? So we knew about the f inverse function that was given. Its domain is x greater than or equal to -4, and its range is y greater than or equal to 0. That means for this parabola, I can't take this whole parabola. I just need one side of this parabola so that it's 1-to-1 and so that its domain agrees with the range of the inverse that we had. So I only want the right side of that parabola. And then I can see that these two functions appear to be inverses of each other because they are symmetric across that line y equals x. Okay, so we've said, hey, this function g, that happens to be the inverse of x squared minus 4, at least for x greater than or equal to 0. Using that idea, I can say, well, then the derivative for this f inverse, which is the derivative we're trying to find, by this formula says that's the reciprocal of, or 1 over, the derivative of my original function evaluated at the inverse function. And I can say, well, the derivative of f would be 2x. So the derivative of f evaluated at the inverse function would be the same thing as the derivative with the input square root of x plus 4. And that would just be simply 2 times square root of x plus 4. So the reciprocal of f prime at f inverse of x would be 1 over 2 times the square root of x plus 4. Right? So that's using the theorem. We can find the derivative of square root of x plus 4 that way. And then we can also try to find that derivative without using the theorem. So evaluating the derivative of square root of x plus 4 directly, we would need chain rule because we have the square root with another function inside of it. We would say, all right, that's the derivative of x plus 4 to the 1/2, just rewriting. And so we would say, well, that's going to be, use the power rule to differentiate the power of 1/2, leave the x plus 4 just as it is. My new exponent will be a half, negative a half, and then I want to multiply by the derivative of the inside, which would just be 1. And if I rewrite, that's the same thing as 1 over 2 would stay in the denominator, and then I would have the square root of x plus 4 also in the denominator. Right, so we can use the theorem to find the derivative of square root of x plus 4, or we can just evaluate that derivative directly. We can see, thankfully, that we get the same result either way. But we can also see that just using the chain rule is much simpler for this particular derivative that we're trying to find. All right, then I'm going to just rewrite this theorem that we had. The derivative of the inverse function is the reciprocal of the derivative of the original function evaluated at the inverse function. And we'll be using that on this page, so I just wanted to rewrite it. Okay, so example 2 says if f is x squared plus 4 for x greater than or equal to 0, find the inverse, and then also compare the slope of the tangent line to the graph of f at the point 2, 8 with the slope of the tangent line to the graph of g at the point 8, 2. And I don't know why I typed g there, but by g I meant the inverse function, so f inverse of x. Right. So I'm wanting to compare the two at points where the x and y are switched, so at points that would kind of correspond to each other in that f inverse pairing. So this isn't hugely different from the last problem, but instead of looking at the general derivative, we're just looking at derivative at specific points. So if f is x squared plus 4 for x greater than or equal to 0, it helps, I think, to make a quick sketch of f, and that will allow us to make the right choices when we are looking at the derivative. So x squared plus 4, so parabola shifted 4 units up, but only the right side again, because it says x greater than or equal to 0 only. So I can just picture what the graph of the inverse will look like. I can see that it has to be the graph of f reflected across the line y equals x. So I know I'm going to have the point 4, 0, and I know this is going to look like a square root function, shifted 4 units to the right. So if I find the inverse, I switch x and y, and then I try to solve for y. I would have y squared equals x minus 4, and then I'd have y equals positive or negative square root of x minus 4. And I know that a function can't have both positive and negative. It can't be one or the other. It has to just be one of them. And from the way I know this graph needs to look, I know that I need to choose the positive square root. If the domain for f had been restricted to x less than or equal to 0, that would mean I would choose the negative square root here when I'm trying to find the inverse. But as it is, we want the positive square root. So we can say the inverse function for the function that was given would be positive square root of x minus 4. All right, so then it says compare the slope of the tangent line to the graph of f at the point 2, 8. So that phrase, we will find that by doing the derivative of f when x equals 2. And I can see that the derivative of f would just be 2x. So instead of just 2x, I'm just going to go straight to filling in the x equals 2. And so that should be 4. And what I want to find then next is the derivative value instead of the function value. The derivative, the inverse derivative when x equals 8. And the inverse derivative at a general x, again, this is similar to what we just saw. We would use the chain rule. We'd have 1/2 x minus 4 to the negative 1/2 times the derivative of the inside, which is just 1. So at x equals 8, I will have 1 over 2 times the square root of 8 minus 4. And so we'll have 1 over 2 times the square root of 4. That's 1/4. And that's exactly what we wanted to find because that's the reciprocal of the derivative of the original function at that corresponding point where we switch the x's and y's. All right, then example 3 is the first time we'll actually need to use this theorem to find the derivative we're wanting to find. It'll be more efficient than trying to find the inverse function itself. So this is saying for the function x cubed plus 2x plus 3, find the inverse derivative at 0. So the first thing to observe is that it is challenging, not impossible, but definitely challenging to solve for f inverse of x. You can try to do this, switch the x's and y's, and then solve for y, but it's going to be kind of rather messy. So, since we don't need the derivative at, or the inverse derivative at every value of x, we only need it at 0. We can say, let's put the pieces together that we need according to that theorem. So this would say the inverse derivative at 0 is the reciprocal of the derivative of the original function at f inverse of 0. So to find the value I'm looking for, I need to determine what f inverse of 0 is, and I need a formula for f prime of x. F prime of x will be easy, right? That's just 3x squared plus 2. And I don't need, again, I don't need a formula for f inverse. I just need to know what's f inverse of 0. So this 0 here, this is an x equals 0 for f inverse. That means that's a y equals 0 for f, right? So I'm thinking, okay, for the original function f, if y equals 0, I need to find the x that corresponds to that. And I can, again, it's not an easy equation to solve, but it's something I can just figure out by looking because it's going to be a fairly nice integer value solution. I can notice that if x is 1, I would have 1 cubed plus 2, and that's 3, which is close because I want opposite of 3. So I can say, if x is a negative 1, that's going to work, right? Because if x is negative 1 cubed plus 2 times negative 1 gives me negative 3. So I had to think a little bit, but I was able to just look at that and find a value, right? So what I know is when on f, when x is negative 1, y is negative 3. So that means for f inverse, excuse me, not y equals negative 3, y equals 0. So for the inverse function, when x is 0, y is going to be negative 1. So f inverse of 0 is negative 1. That means what I need here is 1 over the derivative of the original function at negative 1. So I want 1 over, if I put negative 1 into the original function, it looks like I get 5. So 1 over 3 plus 2, so 1/5. Right? So without actually finding the inverse function and without finding the inverse function derivative at every x, we're still able to find the derivative of the inverse at this specific x equals 0. Okay, now to the real task at hand. We're hoping to find the derivatives for a family of functions whose derivatives we don't know yet, which would be the inverse trig functions. So let's find the derivative for arctangent of x. All right, so the derivative for arctangent of x we're hoping to show is 1 over 1 plus x squared. And the hint is let y equal arctangent of x. We're going to solve for x, differentiate both sides, and then use right triangle trigonometry. So if y equals arctangent of x, our goal is to find dy dx. All right, so if I solve this for x, I have x equals tangent of y. And then when I differentiate both sides, I'm thinking of x as the variable. And so I have the derivative of x would just be 1. And notice here I have a composition. So I need to use the chain rule when I differentiate. So the derivative for tangent is secant squared. And I would leave the inside just the same as it was. So let's say secant of y squared times the derivative of the inside. And I don't have the derivative of the inside, but I can write it in symbols as dy dx. Right, that's a way to write the derivative of y with respect to x. So I just said I'm going to do the derivative of the outside, which was tangent, and leave the inside the same, and multiply by the derivative of the inside. Okay, so now I can say dy dx is 1 over secant of y squared. And then I can say, but that looks complicated because the secant in the denominator is the same as cosine in the numerator. So now I can say the derivative of y with respect to x is cosine of y squared. But I don't want y's in my answer, I want x's in my answer. So let's make a picture. And our original assumption was that y is arctangent of x. And then so we said that means tangent of y is x, which I'm going to write just for emphasis as x over 1. And what I want to remember is that tangent is the ratio of the opposite to the adjacent sides of a right triangle. So I can make a sketch here, and that the y is going to be my angle, and the x and 1 are going to be sides relative to that angle. So if I make a sketch of a right triangle, I've got a 90-degree angle, and then I have this angle that I'm going to call y. And if that is y, then x needs to be the length of the opposite side, and y needs to be the, or excuse me, 1 needs to be the length of the adjacent side. And then by Pythagorean theorem, I can say the hypotenuse will be the square root of the sum of the squares of the other sides. So this will be 1 squared plus x squared. Right, so Pythagorean theorem would be used there. Right, and now what I'm wanting to find is cosine of y. And cosine of y, I want, let's see, adjacent over hypotenuse. So adjacent is 1, and hypotenuse is square root of 1 plus x squared. And then if I go back to my derivative, I will have, using the sides that we just found, 1 over square root of 1 plus x squared, that quantity squared when I have cosine squared. So we are finding dy dx is 1 over the square root of 1 plus x squared squared. And that shows us that the derivative of arctangent of x, since that's our y, is exactly 1 over 1 plus x squared. So that's a way to show that the derivative for arctangent is 1 over 1 plus x squared. And the derivatives for the remaining inverse trig functions can be established along those same lines, just using the same techniques. But I'm not going to require that you go through those. I'm just going to ask that you memorize these. And really, the ones that I need you to memorize are maybe not all 6 of these, although there are patterns that make it not so bad. I would say focus on these 3 for arcsine, arctangent, and arccosine. So those 3 to focus on. Then let's just use these in some examples. So in example 5, we want to differentiate x times arcsine of x cubed. Notice here I have a product, because when I was reading that I had to say times. So I'll need a product rule, and then I also am going to need a chain rule, because I have not just arcsine of x, but arcsine of x cubed. Right. So when I'm finding the derivative for this function, I'm thinking the first function times the derivative of the second, and I'm just going to sketch this out. Plus the second function times the derivative of the first. Right? And the derivative of the first, that's going to be simple. That's just 1. The derivative of the second, that's the one that's going to be a little bit more work for us. So let's think this through. So I want x times, and the second is a composition of arcsine and x cubed. So I do the derivative of the outside function using the inside function as its input, right? So the derivative for arcsine of x is 1 over square root of 1 minus x squared. So I'm going to have the derivative of 1 over square root of 1 minus, instead of x squared, I want x cubed squared, times the derivative of the inside, which would be 3x squared. Then we'll have plus arcsine x cubed times 1. So if we want to clean this up a little bit, we'll have 3x cubed over square root of 1 minus x to the 6th plus arcsine of x cubed. All right, next one we have, this time just a composition. There's not multiplication anywhere, there's not division anywhere, but the composition has 3 layers instead of just 2. We have a square root function on the outside, arctangent in the middle, and then 2t plus 5 as the innermost function. So when we do this derivative, we're going to have 3 factors. First we'll have, I guess let's go ahead and rewrite g as arctan of 2t plus 5, that whole quantity, to the 1/2. So we'll use the power rule and differentiate the power 1/2. We'll move the 1/2 down and leave everything else exactly the same. Make a new exponent of negative 1/2. So the input here is going to, again, just be arctangent of 2t plus 5. Nothing changes there. And then on the next line, I'm going to multiply by the derivative of arctangent. Derivative of arctangent, we need 1 over 1 plus the input, whatever that is, in this case 2t plus 5 squared, So that's the derivative of arctangent evaluated at that input function. And then lastly, we need to multiply by the derivative of the inside function, which is just 2. So we've got those three factors, one of them where we differentiated the 1/2 power, one of them where we differentiated arctangent but left its input the same, and then one where we differentiated 2t plus 5. In example 5c, we're asked to differentiate inverse secant of 1 over x. And so while I told you to memorize just the derivative for arcsine, arctangent, and arccosine, I would expect you to, at least on homework and things where you could have access to your notes, be able to do derivatives involving arcsecant, arccotangent, and arccosecant. So I would expect you would look those up and be able to get through them. For an exam where I expect you to have to be just using your brain and not your notes, then I would only give you problems involving arcsine, arctangent, or arccosine. So, but something like this you might see in the homework. Okay, so the derivative for arcsecant of 1 over x, you first differentiate the outside function, which is arcsecant or inverse secant, and we will leave the input just like it is. So again, we're doing chain rule here. And the structure for arcsecant is 1 over the absolute value of the input, which in this case is 1 over x, times the square root of the input squared, so 1 over x squared, minus 1, and then we need to multiply by the derivative of the inside function. Remember, 1 over x is the same as x to the negative 1. So I'll use the power rule, and so that will be negative 1 times x to the negative 2. So if we want to, we could rewrite this as 1 over absolute value of 1 over x times square root of 1 over x squared minus 1 times negative 1 over x squared. And then if we really wanted to, we could clean that up a little bit. We could multiply this x squared with the absolute value of 1 over x. And we could say that's going to be the same thing as, let's see, negative 1, and then x squared multiplied with absolute value of 1 over x. We should get absolute value of x. And then we've got square root of 1 over x squared minus 1. We could go even further, but for now, let's just leave it like that. Our goal was just to get the derivative, so we'll just leave it. In the next couple of examples, we'll need to clean the derivative up to be able to work with it a little better. But for this one, let's just leave it right there. Okay. Then example 6, we have a local movie theater with a 30-foot high screen. It's 10 feet above a person's eye level when seated. It has a viewing angle theta in radians given by this function. And x is the distance away from the movie screen where the person is sitting as shown in the figure. So we don't need to establish that relationship between theta and x is true. We'll just use it. And part A asks us to find d theta dx. And from the previous page, we can go back and look, but d theta, the derivative of cotangent of theta, inverse cotangent. Goodness, I'll get this right here. Derivative with respect to x of inverse cotangent of x is negative 1 over 1 plus x squared. So here, we want the derivative for inverse cotangent of x over 40. So instead of just this pattern, our input is x over 40. So we'll need negative 1 over 1 plus the input, which is not just x, it's x over 40 squared, times the derivative of the inside function. That inside function is just like a multiple of x, so the derivative will just be that multiple, so 1/40th. And then we have minus the derivative of inverse cotangent of x over 10. So that same pattern, negative 1 over 1 plus the input, x over 10, squared, times the derivative of the input, which would be 1/10. All right, so this one we're going to clean up a little bit. Let's see. I'm going to multiply this 1/40th with my first fraction, and that's going to give me negative 1 over 40 plus x squared over 40, because I have a 40 squared in the denominator, and that's getting multiplied with this 40. And then when I add the next term, I'm subtracting a negative 1, so I'll do plus 1 over 10 plus x squared over 10. And let's clean that up even a little bit more. I'm going to multiply the first fraction by 40 over 40 to clear up this complex fraction, and the second one by 10 over 10. So now I can see d theta dx in a clean form will be negative 40 over 1600 plus x squared, and then plus 10 over 100 plus x squared. So now we don't have any complex fractions, and we can work with this. Next, we're asked to find d theta dx for x equals 5, 10, 15, and 20. And I think I have this set up in GeoGebra. Since we're doing a bunch of values, it's easiest if we just look at a table. And we're asked to do first 5, 10, 15, and 20, and then we're asked to do 25, 30, 35, and 40. So I have, I think, all of these here in this table. I can see when x is 5, d theta dt is 0.055. When x is 10, we have 0.026. At 15, we have 0.0088, and then at 20, we have 0. And then after that, we have negative values, negative 0.004, negative 0.006, and so on, right? And so what we can see, what we want to summarize here as d theta dx is positive for x equals 5, 10, and 15, but d theta dx equals 0 for x equals 20. And then for the values in part D, d theta dx is negative for x equals 25, 30, 35, and 40. And you can see it continues after that, actually. All these are negative. So this means now we're asked to interpret these results for x equals 5, 10, and 15. So when we're 5, 10, or 15 feet away from the screen, if d theta dx is positive, that means when x increases a little bit, theta will also increase a little bit. So theta increases as x increases. But for the values in part D, 25, 30, 35, 40, and so on, as x increases, theta decreases. So as we move further away, our viewing angle would decrease. But for those values 5, 10, 15, that means as we move further away, our viewing angle would increase. So it seems that x equals 20 would be the best spot. That spot where the derivative switches from positive to negative. So up ahead of x equals 20, if we increase x a little bit, our angle is getting bigger. Once we pass 20, if we increase x a little bit, our angle is shrinking. So it appears we would want to sit 20 feet away for the maximum viewing angle. So we're looking for that spot where d theta dx changes from positive to negative. And we want to sit in that spot. And example 7, a building that is 225 feet tall casts a shadow of various lengths x as the day goes by. At an angle of elevation, theta is formed by the lines from the top and the bottom of the building to the tip of the shadow, as shown in this figure. And we want to find the rate of change of the angle of elevation d theta dx when x is 272 feet. So this is similar to the last problem. We're looking for a rate of change of an angle, but this time we have to come up with a function that relates the angle and x. So we can see here that relative to angle theta, we have the opposite side and we have the adjacent side. So we could set up either tangent of theta is 225 over x, or cotangent of theta is x over 225. Either of those would work. And then if I solve for theta, I have theta is inverse tangent of 225 over x, or theta is inverse cotangent of x over 225. Either of these are going to require the chain rule when we do the derivative. And so what I'm thinking is I would rather do the derivative of x over 225 than I would the derivative of 225 over x, just because that's going to get a little more complicated because I'll have an x to the negative 2, and the derivative for x over 225 is pretty straightforward. So I would choose this one, but really either way is totally fine. If we choose this, we'll have d theta dx equals negative 1 over 1 plus the input squared times the derivative of the input, 1 over 225. So very similar to what we just did on the last problem. And again, we can clean that up a little bit. First, I'll distribute the 225 to both terms here, and I'll have negative 1 over 225, and that will be x squared over 225. Again, I have 225 squared in that denominator. I'm multiplying by one factor of 225, so one of those is going to be reduced. And then, to clean up the complex fraction, I'll multiply by 225 over 225. And so I'll have d theta dx is negative 225 over 225 squared plus x squared. So that's d theta dx, and then we want this when x is 272. So if we plug in 272, let's see what we get. So now we want to evaluate, let's see, negative 225 over 225 squared plus 272 squared. And so we get approximately negative 0.0018. And this would be in radians per foot, because our output would be in radians for the angle, and our x, the input, was feet. So when x is 272 feet, the angle of elevation is decreasing at a rate of negative 0.0018 radians per feet. And technically, since I already said decreasing, I don't want to say at a rate of negative. I would say it's decreasing at a rate of 0.0018 radians per foot, because the negative sign is encompassed by the already saying that it's decreasing at that rate. So there we go.